Hi, so we are all here. Are you ready to go?
Yeah, I'm good to go.
Okay, then welcome back everybody to the online seminar. The first speaker of this fall is Alex Deibel. He did his PhD at MSU and is now at Indiana. And he will talk about nuclear astrophysics with accreting neutron stars. And before we begin, two reminders. If you have questions, please wait until the end. And please mute your microphones. Okay, please go ahead.
Hey, everybody. So today I'm going to talk about what we can learn about the dense matter of neutron stars, mainly using observations of neutron star cooling. And this is work that we've been doing for quite some time with several people at JINA, and really the JINA-sponsored meetings we've been having have been really helpful in finishing a lot of this work. Some of it you'll have seen before, but I've added some new stuff near the end, which I hope to get to. Okay, so, oops, sorry. So when I talk about neutron star cooling, I'm talking about the cooling crust, which is essentially the outermost kilometer of the neutron star. And because these objects have, a solar mass of material or more packed into something that's like 11 or 12 kilometers, the crust is a very dense environment. And the sources we're looking at, so the actual observations we're using to probe these regions, are cooling neutron stars in low mass X-ray binaries. So in this type of system, you have a neutron star and some main sequence or giant companion that's less massive than the neutron star. Material overflows the companion's Roche lobe and creates an accretion disk around the neutron star. And sporadically, we see material from the accretion disk fall onto the neutron star surface. And that's what we call an accretion outburst. They can last, from weeks to years. And some of the sources we have had an outburst that lasted, a decade or more. So how you can think about it is that you're seeing X-rays from the accreting material, that is material that's falling from the inner parts of the accretion disk onto the neutron star surface. So over here I made a pretty simple diagram to just explain this, that material will fall from the accretion disk and emit its gravitational binding energy. And those energies are on the order of X-rays. So we see X-rays from these sources. So this is what it'll look like in outbursts. And then when that accretion just stops falling onto, when that material stops falling onto the neutron star surface, that's called quiescence. And this is the time period when we see neutron stars cooling. Okay, we see the thermal component from the neutron star and then a power law X-ray component from the accretion disk X-rays. So let me just show you an observation of one of these accreting and cooling neutron stars. So these are three instruments, and these are X-ray photon counts as a function of time in days. And I like to look at the swift light curve here, but the source is called MAXI J0556. And so they caught it in outburst, and these cameras slewed to the source. And it accretes at near Eddington, the Eddington accretion limit, for about 460 days, and then accretion stops and decays for about 2 weeks. And then from then on out, we're seeing X-rays as the neutron star cools. And these vertical lines indicate the times when the neutron star was imaged with Chandra. And we have X-ray spectra from those observations. Okay. just to zoom in here, so you can see that already that you're watching a neutron star cool with time. At least that's how we model these things. Okay, so the idea is that these neutron stars get heated up during accretion, their crusts get hotter, and in quiescence, they just cool like a cooling slab. So here are some known sources. I like this plot. It shows you the types of sources we're seeing. That source I just showed you, 0556, is the hottest known transient in that it was the hottest at the outset of quiescence. And these units are just temperature units in EV. We don't know the gravity of the neutron star. That is, we don't know its mass and radius. So we calculate the temperature at infinity. And this is just time in quiescence since the start of quiescence in days. All right. So we reproduce these cooling light curves using our neutron star thermal evolution model. It's just a 1D model. So let me explain the layers of the neutron star crust. Okay, so you have, so this is all about 1 kilometer here, the outermost kilometer of the neutron star. You have, iron group elements in the outermost layers as that accreted material, usually hydrogen and helium, is either burned or processed to higher, more massive elements. It's a liquid plasma at lower densities, and then about 10 to the 6, a little bit more than that, all of those, neutron-rich and iron group elements crystallize into a lattice and just separate themselves based on their charge. And there's an additional electron gas component surrounding that lattice. At greater depths and higher mass densities, there will be an additional component from a quasi-free neutron gas that coexists with the lattice and those degenerate electrons. And then one of our newer additions to the model is the possibility of a nuclear pasta phase, and that's where at these very high densities, close to the crust core transition, the nuclei in the lattice are distorted into various shapes. All right. Oh, so yeah, I forgot I have this. So this, I feel like it's a good example of a lattice. It's just what you might expect, these nuclei separating themselves based on the charge. And then the nuclear pasta, this is just one possibility. There are all sorts of configurations of nuclear pasta, and I'll show some more later. And that'll be relevant for a discussion in a second. Okay, so we build that model and keeping track of all of the thermal properties of each layer, and we model the outburst. So the length of the outburst at a certain accretion rate determines how much material is compressed and how much the crust gets heated out of equilibrium. So I have a simple movie I know I've shown before that demonstrates what's happening during accretion, why we think these crusts heat up in the first place during an outburst. Basically, material accumulating on the surface compresses pre-existing material to higher densities, and that also compresses them to higher chemical potentials in that electron gas and in the inner crust, the electron and neutron gases. And that triggers non-equilibrium nuclear reactions like electron captures, neutron emissions, and even piconuclear fusion reactions, all of which heat the neutron star crust on the order of 2 MeV per accreted nucleon combined from these sources. Okay, and we keep track of the thermal evolution of the entire crust as once it enters quiescence, we will watch it cool by just solving the thermal diffusion equation, right? Because we know the composition of these different components, we know the specific heat of each layer, as a function of density and thermal conductivity as we go deeper. Okay, so in this plot, I want to point out that these units are just column density. You can think of it as a proxy for depth or density. So this is the top of your crust, closer to the surface. And down here is the crust core transition, all right? And this is, let's look at this top panel first. This is the crust temperature profile as a function of time and quiescence. So it starts off up here and it cools as you go to later times in quiescence. And notice here's the thermal time in days as a function of depth. So it takes longer for heat to diffuse to the surface when that heat is stored deeper in the crust. So we're really watching heat diffuse to the surface and keeping track of that. And at later times, we're seeing heat from deeper regions, right? So as the crust cools, this heat that we're seeing, so this is a light curve. These are the observations of 0556 in quiescence, these black data points, okay? And so at the beginning part of this light curve, you're seeing heat diffusing from shallower layers, and then the heat you're seeing at the surface is diffused up from the deep interior, and then eventually you reach the core temperature, which we don't know a priori. So the whole crust thermally relaxes back to the core temperature, right? And I'll just note that these data points are thought to be residual accretion points. So they happen to observe this object when it was accreting a slight amount of material, and it must not have been for long because the source resumed the same cooling trend after both of these points, okay? So you can, in a sense, ignore these. So we fit this light curve by just following the diffusion of heat to the surface as time goes on in quiescence. Now, this is a little rough, but it's to give you an idea of what you're looking at. So based on the thermal time, when you're looking at the light curve at these different periods of time in quiescence, you're seeing heat from those respective layers of the neutron star crust. And you can see that if we want to learn about the denser regions of the crust, we need to have observations at late times, greater than hundreds of days into quiescence and even thousands of days into quiescence in order to probe those regions and their thermal properties. Unfortunately, a lot of these sources will go back into an accretion outburst before they've cooled back to thermal equilibrium with the core. And there are only a couple of cases where we actually have late time observations after 1,000 days. And this also serves to demonstrate that modeling these light curves has several systematic uncertainties. I mean, we know relatively well the composition of the outer crust, so this region. And because we know the composition, we know the specific heat of the components and thermal conductivity, even for accreted compositions of the crust. Of course, these sources should have accreted composition, so after many outburst cycles, they've replaced their crust, perhaps over millions of years, and from all of that accreted material. But things start to become more uncertain, and once we get into the inner crust, namely good models of the accreted composition in the inner crust, because things become quite difficult once you add in that neutron gas. But I know some JINA members, Jonas Lupiner and Ryan Connolly, are working on some models with his code Skynet to follow accreted material using reaction network once it reaches the inner crust, once it's compressed to the inner crust, to see what that composition might be. And furthermore, we don't know the thermal properties of nuclear pasta entirely. And lastly, I would say in terms of this red shifting, this light curve, because we're seeing light that's already been red shifted. So when those X-rays leave the surface of the neutron star, they're red shifted by the gravity. And so we fit these light curves by tuning it and finding a mass and radius and a crust thickness that fit the shape of this light curve, because as you change the gravity, you're changing the crust thickness, and that changes the shape of these light curves. So the whole light curve is very degenerate with all of these parameters, but we're going to move forward, with still trying to constrain what we can about the interiors. So I want to talk about this particular source. So this is some of our most recent work. This source is great because it's one of the ones that has these late time measurements where we can start to learn about the thermal properties of the inner crust and perhaps a nuclear pasta phase. So this source was an outburst for, I believe, about 2.5 years, and not at the Eddington accretion rate, about a 10th Eddington, which means it's not the hottest source when it entered quiescence. But what's good is that it's cooled for a very long time. Oh yeah, so this is just X-ray photon counts as a function of time. You can see here, it's sitting there, and then we see it go into outburst for the 2.5 years, and then it enters quiescence again, all right? And again, these vertical lines are pointings from Chandra and some other telescopes. All right, so here are the observations we have of this source at these times. And you can fit a model fairly well to this without nuclear pasta. And you can see that it plateaus, as you might expect, as the crust reaches the core temperature. It reaches thermal equilibrium with the core once more. And again, the core temperature is just chosen in order to match this plateau. All right. Well, things started to get complicated when we had a more recent observation of this source. Before it went into outburst again. Now it's an outburst, I believe. But this is the last observation we had of the quiescent period of this neutron star. And you can see it's below this curve. It's below the plateau. So we thought, it was unique, that it had returned to equilibrium with the core. And all of the heat had reached the surface. But it looks, this data point is consistent with the change in neutron star surface temperature, but it's also consistent with the change in absorption column between us and the source. So when the X-ray observers modeled the X-ray spectra to get these temperatures, they assume an amount of hydrogen absorption in the direction of the source. And there's no reason to believe that remains constant. So if you keep that the depth of that hydrogen column of gas the same, the amount of material the same, this would be a measurement of the neutron star temperature. But that's not necessarily the case. It's not necessarily constant. But we decided to move forward with assuming it's a drop in neutron star temperature and see what would be required in the deepest regions of the crust in order to fit such an observation. Okay. And so we decided to add nuclear pasta to our model at densities very close to the crust-core transition. Here you can see several different shapes of the nuclear pasta. And I probably like the anti-gnocchi the best because it's like the inverse of a nuclear lattice. It's very interesting, or the anti-spaghetti. So these are just nuclei deformed into these shapes. Well, why we think nuclear pasta can help explain this observation is because it might introduce a layer of low thermal conductivity, especially if there are these structural defects. In particular, Chuck Horowitz in a 2015 paper showed that there are these spiral defects that can occur between layers of lasagna, I believe, and these could act to lower the thermal conductivity by scattering electrons, because the heat is primarily transported by those degenerate electrons which live through the entire crust, and in the inner crust, heat is transported by electron impurity scattering, which I'll explain a little more in a second. And you can think of it in terms of a qualitative explanation. You can think of it as there's going to be a lower thermal conductivity for those electrons if they experience more collisions with anomalies in the lattice. So if it's not uniform, or more anomalies in the pasta. Okay. So we put in a layer just above 8 by 10 to the 13 grams per cubic centimeter, and that's what in the crust core transition we have at about 1.5 by 10 to the 14 grams per cubic centimeter. So it's just at the base of the crust and blends into the crust core transition. At least that's how we modeled it. And you can see, so here's again the old fit without pasta. Now, if you put in that pasta layer, a good fit, you get a good fit with an impurity parameter of 20 and an impurity parameter for the rest of the crust of 1. Now, the impurity parameter is, it encapsulates the composition's effect on the electron conductivity, the thermal conductivity from electron impurity scattering. So if there are more impurities, that means if there is more than one type of nucleus at a given depth, the electrons won't see a uniform potential and they'll scatter off of impurities. So the higher this number, the lower your thermal conductivity is. All right. So you can see previously it was fit with still a relatively low thermal conductivity for the crust. It was just, we used about 3, a little less, for the entire crust. Now, to get a fit with pasta, you need a large pasta layer, a large impurity parameter for the pasta layer. So a very low thermal conductivity layer. And you need a low impurity parameter, so a high thermal conductivity for the layer. And I know this black curve doesn't look like the greatest fit, but that's, I think in the final publication, I put in a better fit, but it shows you what happens when you add this pasta, all right? But why does pasta do this? Is it just the low thermal conductivity that allows it to cool at these late times and continue cooling, thousands of days into quiescence? Well, in fact, we found the reason for this extended cooling that allows us to fit that late observation is there are really 2 reasons. One is the pasta and the low thermal conductivity, and the other is your choice of the neutron superfluid pairing gap. All right, so let's just look at this top panel right here. So this is again a crust temperature profile. This is the crust temperature in black. All right, and this is the inner crust. You see, this is actually the beginning boundary of the inner crust neutron drip. And we have our crust core transition, I believe, at 1.5 by 10 to the 14 grams per cc. Okay, so this is the inner crust. And this gray line indicates where we've added this pasta layer. Now, if you choose, the pasta layer keeps the temperature in this region higher than it normally would be in quiescence. Normally it would slope like this. But so if you choose a pairing gap model that closes in the crust, you can actually get a layer of normal neutrons. So this pairing gap model, this is the critical temperature for neutron superfluidity. All right. So if the crust temperature is above that, you'll have normal neutrons, and if it's below that, you'll have superfluid neutrons. So throughout most of the crust, inner crust, you have superfluid neutrons. However, if this gap closes, so to speak, in the crust or in the pasta layer, a normal neutron layer forms, and that's here in blue. This is the specific heat of normal neutrons. All right. So you can see there's a little layer of normal neutrons at the outset of the inner crust. Then it's superfluid, and then you have another layer of normal neutrons. And the normal neutrons have a relatively high specific heat, and so they store a lot of heat during outburst. And that heat is released at late times in the light curve, thousands of days into quiescence, because of the long thermal time of that neutron layer. So it has thermal times on the order of 4,000, 5,000 days. So at late times, you can see the heat being released from the normal neutron layer. So instead of plateauing, it continues to release heat from the normal neutron layer. All right. So on top of all of the degeneracy we already have in the modeling of these curves, now we have an additional set of parameters, whether the impurity of a pasta layer, assuming a pasta layer is there, and the neutron pairing gap model, which is theoretical and uncertain. And I should also note that you can equally well fit the observations with pasta or without pasta. So say you, even including this temperature measurement, if you make a model that plateaus here, you still get a statistically good fit compared to one that slopes through these points and connects up here. So in summary, you can fit observations with and without pasta, and we've tried other sources as well. All right, but we decided to move forward looking at, let's say pasta's there. What could we learn about the superfluid pairing gap model if we wanted to? Okay, so here are different pairing gap models and their associated light curves. So, here is temperature in gigakelvin, and here is, I've zoomed in on the nuclear pasta region, all right? And so the curve with pasta I showed you before corresponds to this, actually the black curve here. But you can see there are a couple models for the superfluid pairing gap that close in the crust, in the pasta layer, and several that close at higher densities. So in those cases, you don't have a normal neutron layer. You can see that keeping everything else the same, including the pasta impurity parameter and the temperature and the gravity of the neutron star, and just changing the pairing gap model to see the effects on the light curve here. You see that the ones that close in the crust do what we traditionally have for these light curves. They cool and then plateau. And then ones that close in the crust do the sloping at late times, the late time heat release from the normal neutron layer. All right. So we thought, well, in a sense, where these, if we want to look at a normal neutron layer and maybe seeing if the observations can constrain how large this normal neutron layer is, and that will allow us to empirically sort of constrain which singlet pairing gap model is preferred by these cooling neutron stars. Okay, and so in order to do that, we made a model where the closing density, so by closing density, I mean where this really drops down here and the crust temperature is larger than the critical temperature. So wherever that density is will determine the thickness of your normal neutron layer. So for instance, this blue curve here, this pairing gap that closes at the lowest densities, it has the thickest normal neutron layer, right? Because there's more space between the closed and the crust core transition. And that's why it has more heat stored and is hotter in quiescence at late times, right? So this is some work I've been doing with Ryan Connolly. Now, this is just to demonstrate in a source that's been accreting for a long time. Sorry, I didn't put units here. These are densities in grams per cubic centimeter. So a source like the one I just showed you, this MXB 1659, an accretion rate of about 10th Eddington for 10 years, the entire crust has time to reach a steady state. And you see the familiar result, or at least the one I just showed you, that if this closure density of the pairing gap is shallower, you get a thicker normal neutron layer at the bottom of the crust. So these curves up here, the lighter gray ones, this is the shallowest closure density, and then increasing closure densities for the pairing gap, right? And you can see a slope difference, a shape difference in terms of these light curves, depending on the thickness of that layer. Of course, all of these assuming the same impurity of 20, again, for the pasta. Well, when things, so in looking into this, you know, not all sources reach steady state, and things start to get complicated when you look at a source that accretes for a shorter amount of time. So this would be for like MXB, for instance, the one I just showed you. Again, same closure densities here. You see that the crust hasn't had time to reach a steady state. That means all of that deep crustal heating, like from piconuclear reactions and things like that, hasn't diffused into the outer crust like it normally does. Instead, a lot of it's being stored in the pasta layer and in the normal neutron layer. So when you have, that's why the shallowest closure density over here, which gives you the largest normal neutron layer, actually has a cooler inner crust and outer crust at early times in the light curve, because now heat from below hasn't diffused upward. But it still has the largest heat release at late times from the normal neutron layer. Okay, and so depending on the core temperature you choose, you can almost, in effect, reproduce a plateau of a similar nature, one without, similar to a model without pasta normal neutrons. You can get a similar appearance by adjusting the thickness of your normal neutron layer, in essence, choosing a superfluid pairing gap model that best fits your observations. So this is currently where we're at working. So the fits to MXB, we recently had published in AppJ. It's work I did with Ed, Andrew, and Sanjay. And this is preliminary stuff I'm working on with Ryan on perhaps empirically constraining in some way this pairing gap model by just using these late time observations and the shape of the light curve. And because the model is degenerate with so many parameters, I'm likely going to run MCMC simulations that test various values of these parameters. So in MCMC, right, it just runs a set of parameters, checks the fit to the observational data, and then tests new parameters. and you'll get constraints on the parameter space and what values likely best fit these curves. And I'd be interested to see, what the observations might say for various choices of thermal conductivity for the pasta layer, which is still uncertain, as well as various choices for the transition temperature, or the closure density of the superfluid gap. So that's something we're working on now. And furthermore, it will be helpful to have remove one of these parameters entirely, and that's the composition of the inner crust, using, when Ryan and Jonas finish work on the accreted neutron star inner crust using the reaction network, we should be able to just put that in the code and not have to vary the impurity parameter of the crust like I showed you earlier. Instead, only have to worry about varying the impurity of the pasta layer. Okay. So in the end, what we've seen is that you can fit these observations fairly well by just, using our simple model that treats the crust as a cooling slab without nuclear pasta, or worrying about the superfluid pairing gap model. You can still fit most of these observations, only a couple though have these late time observations. But we find that you can fit them as well when you include pasta, which we think perhaps should be there or is likely there, but we don't know its thermal conductivity, and we don't know what pairing gap is correct. So once you add in pasta and that pairing gap, you have additional uncertainties in fitting these light curves. So we'll have to go back and look at these light curves we've already fit and the constraints on the composition we've already found, and see how those constraints change when we add in pasta and a normal neutron layer. And furthermore, because a lot of these sources have, in fact, all of them have different outburst lengths, they're heated different amounts. So some reach steady state and others don't. And that's actually useful when we're looking at constraining, pasta and the normal neutrons, because of their low thermal conductivity and the high specific heat of the neutrons, they can actually prevent heat from diffusing to the outer crust and affect the early light curve. And in terms of further collaboration with JINA, I would be interested to talk with anybody who has expertise on neutron superfluid gap models, to see what they think about if it's possible to reverse engineer an empirical superfluid gap model from these observations in some way. All right, so that's it. Thanks.
Okay, thank you for a very nice talk. Yeah, Andrew has a question. Please go ahead. Should I read it, or do you want to?
You can go ahead and read it.
Okay, so Andrew asks, can you comment on whether or not the nature of neutron pairing in the inner crust at high densities is affected by the presence of the nuclei, and how large this modification might be relative to the change in specific heat that you are describing?
Let's see.
Sorry,
So,
Alex.
yeah, I can hear you. Go ahead.
Does that make sense, or?
What we did is, in terms of the thermal conductivity of the neutrons and I want to say that we've calculated the thermal conductivity of the normal neutron layer and seen that it's actually less than electron conductivity. But that's about all we've done. I'm not sure in what sense the neutrons would be affected by nuclei.
So the neutron superfluid calculations you refer to, right, is Gazarlis 2008 and
Yes,
Schwenk et al.
yeah.
2003, right? Those are pure neutron matter with no nuclei.
Okay.
But in the deepest regions of the inner crust, the nuclei are pretty close together.
Right.
The neutrons, in particular, the nature of the neutron superfluidity may be affected by the fact that there are nuclei not so far away.
Right. Right. Yeah. I suppose I don't have a good intuition for how the neutron gap models, the theoretical models, are derived.
Well, yeah. I mean, to be fair, it's a hard question, and I have no idea how to think about it either, which is kind of why I asked. But yeah, okay. Thank you.
Yeah, and furthermore, I wonder if it would matter if those nuclei are deformed in terms of the gap as well, if nuclei do affect the gap. Anyway.
Okay, there are some questions at OU. Please ask.
Yeah, hi Alex. I have one question, and then I think Mamoon has one as well.
Sure.
The one question I have is, on your second to last slide, you showed this light curve as as a function of time, assuming different densities for where the superfluid gap turns off, and it looked like it affects the curvature as well at earlier times. So could you fit light curves for transients that don't necessarily have the late time data points? Because it looks like you have a stronger curvature depending on at earlier times, depending on where that gap is.
Right. I see what you're saying. It's I would say it would be pretty shaky to just use early observations, because if you fit something without, let's say without positive normal neutrons, you could get a curve that goes cleanly through this, yes. But I don't know how much you mean this slight curvature in these observations? I don't know if you should read, how much you can really read into that. I would prefer to have late time observations to connect, a curve that passes through these points and then later times. Otherwise, you could fit many lines through just these three.
Okay, thanks. Can we ask another and go?
Sure. Yeah, go for it.
So my question is, what goes into calculating the pairing gap and hence the critical temperature? Is it the pairing strength or something else?
Is it the what? Strength?
Strength.
I'm not entirely sure. What I've done is just take the pairing gap models and their critical temperatures as a function of density and put them into the model. I didn't derive them, or I'm not calculating them. I have them in tabular form taken from the literature, and I use them because I'm not an expert on the pairing gap, at least not yet.
Okay. Thank you.
So I'm not sure if I can entirely answer that.
Further questions? Actually, I have one. What limits the amount of data points in the temperature versus time curves you show? I mean, why are there not more data points at late times?
It's just it's the subscription rate to these X-ray telescopes. I mean, this is a Chandra X-ray telescope, and I believe they need kiloseconds of time to get these X-ray spectra, so hours. And it's highly competitive for observational astronomers to use these X-ray telescopes. And so these are as many points as we can get from our X-ray observational astronomer colleagues. And these aren't the only sources they're imaging either. They're taking X-ray spectra of many transients, about a dozen of them or so. So I think it's limited by just the time we can get on those telescopes.
Okay, thank you. There are some more questions at MSU, so please just ask.
A related question. I have to admit, I had to type and I missed the beginning of this question, but
okay.
I had something related. It looks like you want more observations at the end. And
Oh, yeah.
I was just wondering, is there a source in the making right now that's sort of cooling away, that's getting close? And is there a way for modelers to actually predict when the X-ray observers should really start looking more frequently?
No, as far as I know, the sources we have now, I think perhaps one, KS1731, Ed can correct me, I think that one might still be in quiescence, but as far as I know, the others have gone back into outburst. So I think, I don't know if there are any right now that are approaching thousands of days into quiescence.
What about the other sources of accreting near Eddington? 1701. Did that go back into
XTE 1701? I don't remember. I'm having trouble remembering. Perhaps there might. So there may be one source, but no, we don't predict when they go into outburst. They just see an X-ray flare and they slew to it, or an X-ray, outburst, and they slew to it. They're not predicted on by any means.
But MXB is back in outburst, and it will presumably
It's back in outburst.
Quiescent.
Yeah. So this source is done. We have no more.
I mean, you guys are in a great position. I mean, once you have the first points, you can make a model and predict when one should really look.
Yeah.
Right.
Oh, you mean, right, yes, of course. Yes, we can predict when to look once it's in quiescence, but we don't know when it's going to go into outburst or quiescence.
This is 1,000 days. That's 3 years. That's plenty of time to plan observations.
Yes.
Right, but you could write great proposals now, right?
That's right.
Yeah. Yeah, and furthermore, after 1,000 days, they can be further spaced apart, these observations. And well, eventually, 10, 20 years from now, we will have more data on the same sources going to outburst multiple times. Especially with J0556, I think we have a second quiescent observation with, the group in Amsterdam is working on. So that will help too, to see how the quiescent light curves change between outbursts.
Yeah. So Alex, good to see you again. By the way, Alex, I have a question for you.
Sure.
So the thermal time goes both the thermal conductivity and the specific heat go into it. So you're sensitive as to what the impurity parameter is, as well as the specific heat. But the gradient of the temperature just depends really on the thermal conductivity. So my question is, the curvature in the plot you have up now, the curvature for an outburst of a given length, how much of the degeneracy between conductivity and specific heat does that break? I mean, could you disentangle them and then get both?
That's a good question. I guess I hadn't really thought about it. Right. I suppose so. Right, because the late time cooling from the normal neutron layer, it happens on a thermal time depending on the specific heat and the thermal conductivity, but the diffusion of the heat into the outer crust should more depend on just the thermal conductivity. I'd have to look into it. I guess it never really occurred to me. But I suppose you could somehow delineate the two.
Yeah, that would be nice if possible.
And I also, I'm not entirely sure if, that's why I would like to talk to someone who works on superfluid gap models to know, what is feasible in terms of the shallowest, closure density you could possibly have. Like, what are the sorts of restrictions we have on the pairing gap model?
Any other questions? If not, let's thank Alex again.
Thanks for your questions.
See you all in 2 weeks. Bye.